This new section, we're going to talk about the definition of the Laplace transformation. I think before getting into the definition, should talk about the linearity of integration. If you have the integral of a multiple of f of x, a times f of x, plus a multiple of g of x, b times g of x, you want to integrate this. Well, you have a sum of two functions that you want to integrate. Just because I'm calling f of x a function, that doesn't mean a times it is not a function. This is another function. Maybe it's h of x. With an integral of a times f of x plus dx plus the integral of b times g of x dx. And then you can even pull the constants in front. So you get a times the integral of f of x dx plus b times the integral of g of x dx. This is the definition of linearity with respect to integrals. Now the Laplace transformation is an integral. So we're going to have linearity in the Laplace transformation. Now the definition is, this here is the symbol for Laplace transformation of f of t. Now the integral is always the integral from 0 to infinity of e to the negative st times dt. That part is always there, times f of t. That's the definition of Laplace transformation. Recall that the integral of e to any number times t dt is just e to the kt, the same thing we started with, divided by the multiple of k, or the multiple of t. Well, t is being multiplied by. That's what you divide by, of course, plus c. So let's calculate some Laplace transformation. What's the Laplace transformation of 1? Well, by definition, it's e to the infinity, the integral of 0 to infinity, of e to the negative st times f of t, which is 1, dt. Now, of course, multiplying by 1, you don't have to do. The thing here is, this is an improper limit. Integral. This is an improper integral because of their limit infinity. So instead of going from 0 to infinity, we'll go from 0 to b, and then we'll take the limit as b goes to infinity. So here it is. So it's the limit as b goes to infinity of this. Well, this integral is the same that I have on the bottom, except k is negative s. So I'm going to get e to the negative st, and I divide by negative s. And we're going to go evaluate it from 0 to b. So it's the limit as b goes to infinity. And I want to evaluate this. But that is negative 1. Here's the 1 here. I'm going to keep the s on the bottom. I'm going to bring the e to the negative st to the bottom as e to the st. So I dealt with this. I dealt with this by putting it down here. I dealt with the s, it's in the bottom, it stayed in the bottom. There's a 1 on the top, because I can't just have nothing on the top. There's a 1. Now where did this minus sign come from? Well, the understood positive for the top, divided by a negative in the bottom. Positive over negative is negative. And we're going to evaluate this from 0 to b. Now, I hate evaluating when what we're evaluating is negative. There's a rule that says that you can change the sign of that anytime you want. And boy, I want to. As long as you switch the order of the limits. Instead of going from 0 to b, I'm going to go from b to 0. So this is the limit as b goes to infinity of. First I plug t in, 0 for t. So the power is going to be s times 0, which is 0. And e to the 0 is 1. And then s times 1 is 1. So I get 1 over 1. Sorry, s times 1 is s, of course. S times 1 is s. Minus, now I plug 0 in. So I'm going to get 1 over s e to the sb, because t is b. You get 1 over s e to the sb. Now, we're going to assume that s is positive. So what happens is when when b goes to infinity, that's going to go to positive infinity. A positive number like s times really, really large, because b is going to infinity, is really, really large. And then e to the really, really large is really large. And s, some constant, times really, really large is really, really large. If you have 1 over really, really large, this is going to 0. So you have 1 over s minus 0 is 1 over s. The Laplace transformation for 1 is simply 1 over s. You really should know that. Okay, you really should know that. There'll be a list that I put in a few moments, and you should know all those Laplace transformations. Now, if somebody asks you, what's the Laplace transformation of 5? Well, you should realize that 5 is 5 times 1. And you can bring out the 5. In other words, since we're integrating, if you have this, since L is just integration, this is just a times L of f of x plus curly brackets plus b times the Laplace of g of x. The reason is, I'm hoping, quite clear, because it's really the integral from 0 to infinity of e to the negative st times af of x plus bg of x dx. But this becomes distributing. This becomes the integral from 0 to infinity of e to the negative st times af of x plus e to the negative st times bg of x dx. But continuing at the very top, if you have the integral of one thing plus another thing, you can split them up. It's e to the negative st times a f of x dx plus the integral of e to the negative st times bg of x dx. But that's where it comes together even more. So, even more clearly. We can pull the a out in front. We can pull the b out in front of the integral. Well, this is a, but this here is the same as the Laplace for f of x plus b times this integral. But that's just the Laplace of g of x. So not only did I just state it down here, we went and proved it. Now, back to the last line on the bottom. That's 5 times 1. Think of the 1 as a function. F of x is always 1. The 5 can come in front. And I know the Laplace of 1, we just did it. The Laplace of 1, so it's going to be 5 times 1 over s. It's 5 over s. In fact, if you think about it, the Laplace of any number, any constant, well, think of the constant k as k times 1. You can pull the k out in front, and you get k times the Laplace of 1. But the Laplace of 1 is 1 over s, so now we get k over s. So when k is 5, we got 5 over s. When k is pi, we're going to get pi over s. When k is 37, we're going to get the Laplace of 37 over s. Okay, so we did the Laplace of 1. Let's do the Laplace of t. What is the Laplace of t? A Laplace transformation of any function is the integral from 0 to infinity of e to the negative st times f of t, which is t, dt. So like always, this little headache going around. We can't integrate from 0 to infinity, so we go 0 to b, and then we let b go to infinity. So what is the integral of e to the negative st times t dt? Well, this is one where you should use the spaghetti method. Don't do this the complicated way with parts. Derivatives, integrals. I can take the derivative of that function enough times so that eventually I get 0. And I can integrate that other function as many times as I just took the derivative of that function. The first time through, just write them down. T and e to the negative st. Then we integrate it. So we get e to the negative st divided by negative s. I'll just put the negative on the top. And then we have the derivative of negative st is going to be negative e to the negative st over s. But there was another s there already, so it becomes squared. Now, we multiply that product, and then we take away that product. Positive, negative. Now, each one of those products is going to have an e to the negative st in it. So I'm going to factor it out. So it's that product, which is negative t over s, minus that product, which is negative 1 over s squared. And what that equals, what this equals was this. But we didn't really have this. We just have from 0 to b. So we go from 0 to b, And let's not forget to push b to infinity. So this equals to this here. Take the limit as b goes to infinity. Now, everything in that bracket is negative. I hate it when it's negative. So I multiply it by -1. And then I switch the limit. So I go from b to 0. And let's not forget to take the limit. At first you plug in 0. Negative s times 0 is 0. E to the 0 is 1. I won't write the 1 down. And then you have 0 over s, which is 0, plus 1 over s squared. 1 times 1 over s squared is 1 over s squared. Minus, now we plug b in. I'm going to put, instead of multiplying by that, I'm going to divide by the reciprocal, which is e to the positive st. So I get b over s plus 1 over s squared. Now, exponential functions grow faster than everything. Grows faster than a linear. That is, when b goes to infinity, fair enough, this will be large. Or this should be SB, excuse me. But this will be much, much larger. So that division goes to 0. And a constant divided by e to the positive infinity is going to be, the bottom is going to go to infinity, the top is a constant. So the whole fraction goes to 0. That is, all of this goes to 0. The only thing that survived was this first term. So the Laplace of e to the t, the Laplace of t is 1 over s squared. The Laplace of t is 1 over s squared. Let's look at the Laplace of t squared. Let's look at the Laplace of t squared. The Laplace of t squared, well, it's always integral from 0 to infinity of e to the negative st times t squared dt. And of course, we're going to have this silly game with b going to infinity and calling the upper limit b. But what is this integral? E to the negative st t squared dt. Well, if we play the derivative integral game, I can take the derivative. Let me do it up here. I can take the derivative of t squared enough times to get to 0. T squared, the derivative of that is 2t. The derivative of 2t is 2. The derivative of 2 is 0. I took 3 derivatives. I have to be able to integrate the other function 3 times. So I get e to the negative st over negative s, except I put the s there, the negative there. The integral I meant to say. The integral of this piece, which I'm going to put there, is positive e to the negative st over s squared. And the integral of that will be negative e to the negative st over s cubed. Now, if you notice, each of these products, everything in there underneath, everything underneath the I has e to the negative st. So we know it being this. The limit as b goes to infinity, and it's going to be this product plus that product minus that product plus that product. And each product is going to have e to the negative st. So we're going to have positive, well actually a positive, this product is negative. And when you add a negative, you're really taking away. t squared over s times e to the negative st, which I factored out. Now, this product is positive, so we're supposed to take it away. Minus 2t over s squared plus this product. But that product is negative. You know, like adding a negative 7 is the same as just taking away 7. That's why it's minus. It's going to be 2 over s cubed. And we have to evaluate this from 0 to b. Except everything is negative inside the brackets. So I'll multiply inside the big black brackets, multiply everything by negative 1. And I'll get t squared over s minus 2t over s squared plus 2 over s cubed times e to the negative s squared, e to the negative x t from 0 to b. And I can put this in the denominator as e to the positive st. Okay, so we're making progress. Limit as b goes to infinity. Now, since this should be plus. Since I multiplied inside by negative 1, I have to change the limits. B to 0. So first we plug in b for t. We get b squared over s plus 2b over s squared plus 2 over s cubed all over e to the sb minus, okay, first I was supposed to plug in the 0. Let's actually do that. When you plug in 0, that will be 0, this will be 0, this will be 0, this will be 2 over s cubed. Divided by e to the st. Let's actually write it down a bit neater. So when I plug in 0, I'm going to get 2 over s cubed divided by this, which will be 1. It will be 1. S times 0 is 0. E to the 0 is 1. That's what I get when I plug in 0. Minus, now when I plug in b, get b squared over s plus 2b over s squared plus 2 over s cubed all over e to the sb. This is quadratic in b. This is exponential in b. The bottom's going to dominate. The bottom's going to grow much, much bigger than the top, which means everything in here goes to 0. And all that survives is this, 2 over s cubed. So what we learned is the following. We learned that L of t squared is 2 over s cubed. So let me just put it here. L of 1 was 1 over s squared. L of t was 1 over s squared, excuse me. And L of t squared was 2 over s cubed. Now I'm not proving this. L of t cubed, well, let's see. When the power was 1, in the denominator, the power was 1 more. When you do L of t squared, the power in the bottom was 3. So when you take L of t cubed, the power of s in the bottom will be 4. Now you might say, this is simple. 1, 2, 3. Thing is, you'd be wrong, because 1 is the same as 1 factorial, and 2 is the same as 2 factorial, which is 2 times 1. 2 times 1 is 2. This is going to be 3 factorial. In fact, again, we didn't prove this, but the Laplace transformation of t to the n, well, on top, you'll have n factorial. When the power was 1, you had 1 factorial. When the power of t was 2, you had 2 factorial. When it was 3, you had 3 factorial. When the power is n, you should have n factorial. And in the bottom, you always had an s. You always had an s. In fact, you always have a division line in s. A division line in s. Whatever you do, don't get that wrong. And you also have always had this exclamation mark, the symbol for factorial. What changes is the 1 and the 2 and the 3, but they always matched up with the power. Power is n, I'm going to put n factorial. And in the bottom, the power of s was always 1 more than the power of the t. The power of t is n, it's going to be 1 more. That's the Laplace transformation of t to the n. You could prove this by induction. You can prove this by induction. Okay, so that's another one that we have. Let's do a couple of more. Suppose you have the the Laplace transformation of e to the at. Well, it's always Laplace of any function is always the integral from 0 to infinity of e to the negative st times the function that you're taking Laplace of, e to the at times dt. Now this one is a little bit easier. Since we're multiplying and the bases are the same, we just add the exponents. It's e to the at minus st dt. The limit as b goes to infinity of the integral from 0 to b of e. Now all I'll do here is factor out the the t. E to the a minus st dt. Now that integral is straightforward, because the integral of e to any number times t dt is once again e to that number times t divided by that number. And we go from 0 to b. Now, if I multiply by -1, remember, -1 is the same as 1 over -1. That is, I can multiplying by -1 can be the same as multiplying the top by 1, which is e to the a minus st. I didn't do anything to it. And I multiply the bottom by -1, which is s minus a dt. Sorry, no dt. But since I multiply by -1, I don't go from 0 to b, but rather b to 0. Now, in this problem, s is going to be bigger than a. So that means a is smaller. And after all, if you take away s from both sides, you have 0 is bigger than a minus s. that is a minus s is less than 0. This is negative. Okay, so first let's plug in 0. We'll deal with the fact that it's negative in a moment. First I plug in 0, and e to the a minus s times 0 is e to the 0 or 1 over s minus a minus, now our t is b. Now I'm going to put a 1 there. There's the 1. I'm going to put the s minus a. Now I want to bring this to the bottom, but please remember t is b. If I bring it to the bottom, I have to multiply the power by negative 1. I have to change the sign of the power. I get this. Now if b goes to infinity, since s is bigger than a, that's positive, times a really, really large number. This exponent is super large, and e to the really large is infinity. And whether this is plus or positive or negative doesn't matter. If you have 1 over this really, really large number, it tends to 0. And it'll always be positive, just a little positive. If you have 1 over negative that large number, it'll get really close to 0, but it'll always be a little bit less. But most importantly, is it's always going to 0. So this piece, when s is bigger than a, this goes to 0. And as b changes, this couldn't care less. We get 1 over s minus a. So this is 1 over s minus a. It's 1 over s minus that. So if somebody asks you, what's the Laplace transformation of e to the 5t, you go, oh, it's easy. It's 1 over s minus that number. And that's what you need to study as a student. Because then it becomes almost first grade. Just remember the Laplace of e to the at is 1 over s minus a. You remember that, then you know the Laplace of e to the negative 4t is 1 over s minus that number. And that number is not 4. That number is negative 4. So it's 1 over s plus 4. So you just look at this and say, oh, it's e to the at. It's 1 over s minus that number. And you're done. Okay. Let us do one trig function. What's the Laplace transformation of sine of kt? Well, it's an integral from 0 to infinity of e to the negative st times the function dt. So now we need to figure out what that integral is. What is the integral of e to the negative st sine of kt dt? And this is done by parts. I'm going to call that integral I. This is done by parts. I'll let u equal to e to the negative st. So then du will be negative s e to the negative st dt. Well, if that's u, then this must be dv. dv is sine of kt. So v is, well, we know it's going to be like the cosine of kt, but if you take remember, that when you take the derivative of this, you're supposed to get that. But right now, we're getting this. We're getting that. Well, if you multiply this by a negative, and you have to multiply the other side by a negative, it'll become positive. Well, it's starting dt. It's starting to look like this. If I divide by k, it does look like that. Now, I call this u and that dv. The integral of u dv is uv minus the integral of v du. So with uv is that product, which is negative e to the negative st cosine kt over k minus the integral of v du minus that product. Well, a negative times a negative is going to make it positive. And we have s divided by k in front, because it's a constant. And we have e to the negative st times cosine kt dt. We have this times that. So I have I. Remember, this is I. I is equal to negative e to the negative st times cosine kt over k plus s over k times that integral. Right now, I'm going to put all my energy to figure out what this integral is. And this is an integration by parts problem. I'm going to call that u again. And then du will be this. And what's left over will be dv. You have to remember your integration. This is sine of kt over k. So this integral is going to be u times v, which would be e to the negative st times v cosine of kt over k minus the integral of v du. This times that. Well, it's a negative times a positive, which is negative, which is going to make that subtraction addition. And s over k is just s over k. And then we have e to the negative st, e to the negative st times this piece, the sine of kt. We've already put the k in the bottom. There it is. dt. dt. Okay. So this integral we just calculated. It's e to the negative st, the sine of kt over k, plus s over k e to the negative st sine kt dt. Okay. I see one little problem. Not sure what's going on here. Somehow that was supposed to be minus. Go back if you didn't see the error. Go back and see where that error came from. Okay. So this is supposed to be minus. So now it's all going to come together. It's all going to come together. We have I is equal to negative e to the negative xt cosine of kt over k minus se to the negative st times the sine of kt over k squared minus s over k times that integral. Well, that s over k can come in front of the integral. So we have s squared over k squared times this integral. But that integral is this integral again, which we called I. So now I'm going to bring this to the other side. Here I have 1i, and now I'm going to add s squared over k squared I. And this is going to be negative e to the negative st cosine of kt over k minus se to the negative st sine kt over k squared. Okay. Now, if I think of this 1 as k squared over k squared, then this piece is nothing more than, since it has a common denominator, k squared plus s squared over k squared. Okay. So I divide by that number, k squared plus s squared over k squared, just to get I. But on the other side, it's not friendly to divide by that number. So I multiply by the reciprocal. K over k squared plus s squared. Okay. Now, that was this answer at the very, very bottom. The answer to I was just this integral. That is, it was this integral, except we didn't deal with limits. So now I'm going to deal with the limits. It's equal to the limit as b goes to infinity of, says if that's b. But I know what this integral is. It's on the bottom. I'll just write the k part first. K squared over k squared plus s squared times negative e to the negative st cosine kt over k minus se to the negative st the sine of kt over k squared. And we go from 0 to b. Or I can go from b to 0 if I multiply by negative 1. Now, this really comes in front. It's k squared over k squared plus s squared times the limit of what we get when we plug in the b. Well, first you plug in 0. Well, that'll be 0, and e to the 0 is 1, times cosine is 0, which is 1. So I get 1 over k. Now, I know that this will be 0 when sine of 0 is 0. So you'll have s times 1, which is s, times 0, which is 0, divided by k squared, which is 0. I won't bother writing plus 0. Minus, now I plug b in. I get cosine of k times b. I'm going to put this in the bottom. Well, there's the k in the bottom. And put in the bottom is e to the st, but t is b. Plus same game here, s sine of kb over k squared e to the sb. Now, I know one thing. This is between plus or minus 1. It's a relatively small number. But this is e to the infinity. The bottom's getting larger and larger. When you multiply it by k, it's still, the bottom is still getting bigger and bigger. So what happens is this piece is going to 0. Same argument on top. The sine of kb is going to be between plus or minus 1. Multiply it by s, it'll be between plus or minus s. Divided by k squared, it'll be a constant between s over k, between negative s over k squared and positive s over k squared. But then this is going to infinity, and e to the infinity is going to infinity. The bottom is growing much, much larger than the top. So this is going to infinity, to 0. So what happens is we have k squared over k squared plus s squared times, well, the limit as b goes to infinity of 1 over k is just 1 over k. And everything else is 0. 1 over k minus 0 plus 0 is 1 over k. So here's our answer right here. And I'll do one more step. I'll say this k in the bottom will kill off one of those k's on the top, leaving 1k. K times 1 is k. In the bottom is k squared plus s squared. So what did we just learn? This will be the last one that we proved. We learned that this is k over k squared plus s squared. Now, I'm going to relist some of the ones that we've already done, but I'm going to list others. The Laplace transformation of 1 is 1 over s. The Laplace transformation of t to the n is n factorial over s to the n plus 1. But this was only true when our n are counting numbers. 1, 2, 3, 4, 50 million, counting numbers. And we proved this one, L of e to the at is 1 over s minus a. This one s is bigger than a. And we proved this one just now, the last one we proved, is k over s squared plus k squared. And here's one we didn't prove, the Laplace transformation of cosine of kt. In the bottom is going to be s squared minus k squared. And the top is just s. The Laplace transformation of the hyperbolic sine of kt, or the sinh of kt, is going to be, actually this is plus over here, sorry, this for cosine of kt. For sinh, it's going to be k over s squared minus k squared. And the Laplace transformation of the hyperbolic cosine of kt will be s over s squared minus k squared. So basically, if you know the Laplace of the sine of kt, You should just remember that the Laplace of the sinh of kt, all that differs is the sign. Goes from plus to minus. If you know the Laplace transformation of kt, well, then you know the Laplace transformation of cosh of kt. It's the same as the one above, except the plus becomes a minus. And sinh gets a k on the top, sine gets a k on the top, and the cosine does not, gets the s. How I remember it is, the one that starts with an s, it doesn't get an s on the top. The one that doesn't start with an s does get an s on the top. Starts with an s, don't put an s on the top. Starts with a c, put the s on top. Either s or k goes on the top. One or the other. Okay. So these are ones that you should pretty much just know. You should just outright know those. Now, let's do some others. What if I told you that f of t was a piecewise function? Sometimes it's 4, sometimes it's 0. It's 4 when t is in between 0 and 2, including 0, and it's 0 when t is 2 or more. Find the Laplace of f. Well, we know that the Laplace transformation of f of t is equal to the integral from 0 to infinity of e to the negative st times f of t dt. But f of t changes when it's between 0 and 2, and we are starting at 0. So from 0 to 2, it's 4. But I'm not supposed to just go from 0 to 2. I have to go to infinity. Well, I went from 0 to 2. Now I'll go from 2 to infinity. So I have e to the negative st times the function. Well, when t is 2 or more, the value of the function is 0 dt. And that's 0. And the integral of 0 dt from 2 to infinity. Remember what integral means. It means the area under the curve. Well, the curve is always 0. From 2 to infinity, it's 0. There is no area between the curve and the x-axis. If the function was, say, positive sometimes, only positive, it would be that area. Integral from 2 to infinity of this blue function would be this area. But it wasn't, it was 0. It was always down here. There is no area between that blue line and the x-axis. In fact, it's a rectangle. The base is really long, but the height is 0. It's going to be 0. Okay. Which means, to save space, I'm adding 0, which doesn't do anything. That is, it's this integral. And what I'll do is I'll bring the 4 out in front. So it's 4 times integral from 0 to 2 of e to the negative st dt. But that's a simple integral. It's e to the negative st divided by negative s from 0 to 2. But if I change the sign of this, 4 e to the negative st over s, then I can go from 2 to 0. I can even bring this into the bottom. So when t is 0, I just get 4 over s. Because e to the s times 0 is e to the 0, which is 1. S times 1 is s. Minus, now I put in 2 for t. I get Just write this over, but instead of t, put 2. Get 4 over s e to the s times 2, or 2s. And there is your answer. There is your answer. You want to get common denominators? You can do that. You can multiply by e to the 2s, top and bottom. You can say in the bottom, you definitely have that in common. And on top, you have a 4. So what's left over on top is e to the 2s minus 1. You want to write it that way? That's equally as fine. Okay. Suppose you had the integral of, suppose that f of t was defined sometimes to be 2t plus 1, and other times 0. It's 2t plus 1 when t is in between 0 and 1, and 0 when t is bigger than 1. And we want the Laplace transformation of f of t. If it's more than 1, so we're supposed to go from 0 all the way to infinity. But when it's more than 1, the function is 0. That is, when you do e to the negative st times the function dt, when it's 0, this will be 0, and the integral of 0 dt over any limit will be 0. So we're only going to talk about 0 to 1, and the value of the function is 2t plus 1. Now, I think you should write this as two separate integrals. Integral 0 to 1, distribute, you get 2, which I'll bring in front, t, e to the negative st dt, plus the integral from 0 to 1 of e to the negative st times 1 dt. I won't write the times 1. Alright, so let us first calculate this integral without the limits. We'll do the limits at the end. This is a by parts problem, but I can play the tic-tac-toe method, because I can take the derivative of t a few times and then I get to 0. And I can take the integral of that. First, write it down. The integral will be negative e to the negative st over s. The integral of that will be e to the negative st over s squared. And then it'll be, you add that product, and then you take away that product. And they're both of those products will have e to the negative st in it. So you're going to have negative t over s, and then minus that product, minus 1 over s squared. You want to integrate this, evaluate this from 0 to 1. But I'm going to go from 1 to 0 and change that. In fact, I'll even put this on the bottom like that. But when you plug in 0, this piece will be 0 over s, which is 0, plus 1 over s squared. So you get 1 over s squared times 1, because e to the s times 0 is e to the 0 is 1. So that's what you get when you plug 0 in, minus. Now when you plug 1 in, you're going to get 1 over s plus 1 over s squared divided by e to the s, plus s times 1 is s. So this becomes 1 over s squared minus 1 over s times e to the s minus 1 over s squared times e to the s. And that's what the first integral is going to equal. But please remember that it clearly says to multiply this integral by the number 2. So when I multiply this by 2, I'll get 2 over s squared minus 2 over s e to the s minus 2 over s squared e to the s plus what? Plus this integral. Well, that integral is easy. E to a number times t. The integral of that will be e to that number by t divided by that number. But if I change this sign, then I go from 1 to 0. In fact, this is 1 over s e to the st from 1 to 0. When I plug in 1, that power, when I plug in 0, that power will be 0, and e to the 0 is 1. And s times 1 is 1. So the top is 1, the bottom is s times 1 is s. The bottom is s. Minus, now I plug 1 in. I get 1 over s e to the s times 1. So I get 1 over s minus 1 over s e to the s. And I'm looking for like terms. For example, this and this are like terms. I'm taking away 2 of these. Oops. I'm taking away 2 of these, and then I'm adding a negative one of them. That is, I'm taking away 3 of them. It's going to be minus 3. So we dealt with these 2. And let's not forget the 2 over s squared. Let's not forget the 2 over s squared e to the s. And certainly not, let's not forget to add 1 over s. So that is that problem. Let's try another one. Suppose you come to learn that f of t is e to the t plus 7. Now, here's a problem where you don't need to do any integration. Remember that the Laplace transformation of e to the at is 1 over s minus a. And if you remember that, and you're clever, you don't have to do any integration. So the Laplace of f of t is the Laplace of e to the t plus 7. If e to the t plus 7 is e to the t times e to the 7. But e to the 7 is constant. Remember, if you have L of a constant times a function of t, say, you can bring out the constant. That constant e to the 7 can come out. And then you have e to the 7 times the Laplace of e to the t. e to the 1t. So it's e to the 7 times what this is. But that's easy. It's 1 over s minus 1. e to the 7 times 1 is e to the 7 over s minus 1. I didn't do one integration there. Suppose you come to learn that f of t is a linear combination of trig functions. It's 3 times the cosine of kt plus, 5t. I'm going to give you the k. Plus, say, 2 times the sine of 3t. Well, the Laplace transformation of f of t is the Laplace transformation of f for t. I'm just writing f for t down differently. First, I wrote down f for t that way, now I'm writing it this way. But now we can play the linear game. It's L of this plus L of that. Well, in the L of this, I can factor out the 3. Plus, in the L of that, I can factor out the 2. So this is equal to 3 times this. Well, now remember, that's the one that had s squared plus k squared, where k is 5. And since it starts with a c, I put the s on the top. So it's 2 times L of that. Well, so that is s squared. It's s squared plus 3 squared. Now since this starts with s, I don't put s on the top. I put k on the top. So I get 3 times s over s squared plus 5 squared plus 2 times 3 over s squared plus 9. And there's your answer. Okay, let's try one more problem. Suppose you are given that f for t is the sine of t times the cosine of t. Now, when it comes to these Laplace transformations, you want to try not to use the definition. You're going to remember a handful. I think maybe I gave you 7 of them. Let's actually count them. Call this 1, and then 2, and 3, and 4, and 5. What a good luck when I said 7. You know these 7, you want to try to write any problem that you're given using one of those 7. Now, you should remember that the sine of 2t is 2 sine t times cosine t. You divide the left side by 2, you just get sine t cosine t. You divide, I meant the right side by 2. If you divide the left side by 2, which is the same as multiplying by a half, you get that. That is, this is equal to that. That is, this is 1/2 times the sine of 2t. Well, that's easy then. The Laplace of f for t is nothing more than the Laplace of 1/2 times the sine of 2t. And the half can come in front. So it's just have to know what the Laplace transformation of the sine of 2t is. Times it by a half. Well, it's going to be 1 over s squared plus, that's k, plus k squared. And since this, either s goes on top or k goes on top. Since this starts with s, it's not s that goes on top. It's k. And a half times 2 is 1. So you just get 1 over s squared plus 4. And not doing any integration. You don't want to do e to the negative st times the sine of t times the cosine of t dt. You don't want to do that. You absolutely don't want to do that. Because this is going to keep you busy. In fact, I don't really see how to do this. If somebody asked me how to do this problem, I would replace this with 1/2 sine of 2t. I bring the half in front. It is a negative st times that with the half in front. That is sine of 2t. And we've done integrals like this already. You have to do it by parts 2 times, collect like terms. We've done that one. But you don't even have to do that. You don't even have to do that. Okay? Just know what the Laplace transformation of the sign of kt is. You're going to have in the bottom s squared plus k squared. And since that starts with s, you're going to have k on the top. And in our problem, k is 2. So you have 2 over s squared plus 2 squared. Coincidentally, the 2 got killed off, but that's because we had a number in front. This completes the section on Introduction to Laplace Transformations. Know those 7 like you know your name.